Hello, in this video I'm going to be explaining the properties of binary operations which can be used to define a group. Now, what is a group? Well, a group is a set together with a binary operation that satisfies four axioms. Now, a set on its own is not a group. Now, if G is a set and asterisk is a binary operation defined on G, then G asterisk is a group if the following axioms are true. Now, the first axiom is closure. For all A, B, which are elements of G, then A asterisk B is an element of G. The second axiom is the identity axiom. There exists an identity element, E, which is an element of G, such that for all A, which is an element of G, A asterisk E is equal to E asterisk A, which is equal to A. The third axiom is the inverses axiom. That is, for each A, which is an element of G, there exists an inverse element, A to the power of minus 1, which is an element of G, such that A asterisk A to the power of minus 1 is equal to A to the power of minus 1 asterisk A, which is equal to E. Now, the final axiom is associativity. That is, for all A, B, C, which are elements of G, A asterisk in brackets B asterisk C is equal to, in brackets, A asterisk B asterisk C. Now, there are a couple of crucial things to know. If asterisk is a binary operation, then the closure axiom will be true by definition. So, nevertheless, if asked to show that G asterisk is a group, the closure axiom must still be checked. Now, the notes that I've just shared with you are based on groups lessons, pages 47 to 48, Further Pure Mathematics 2 by Pearson. I have left a link to that book just below my video, so click on it if you're interested. Now, we're going to be using these axioms to show that the set of integers forms a group under addition. We are also going to show that the set of integers does not form a group under multiplication. Okay, so let's show that the set of integers forms a group under addition. Firstly, let's look at closure. The sum of two integers is an integer, so the set must be closed under addition. Okay, let's check the identity element. For all n, which are elements of the integers, n plus 0 is equal to 0 plus n, which is equal to n. Now, 0 is an element of the integers, so the identity element exists. Now, let's check out the inverses axiom. For all n, which are elements of the integers, n plus minus n is equal to minus n plus n, which is equal to 0. Now, minus n is an element of the integers, so minus n is the inverse of n. Finally, let's check out the associativity axiom. A plus, in brackets, B plus C is equal to, in brackets, A plus B plus C, which is equal to A plus B plus C for all ABC, which are elements of the integers. If we take all these axioms into consideration, the set of integers forms a group under addition. Now, you can describe this group as the integers plus. Okay? Now, the last task is to show that the set of integers does not form a group under multiplication. We do this by saying, for all n, which are elements of the integers, n times 1 is equal to 1 times n, which is equal to n. This means that the identity element is 1. However, 0 is an integer, but there isn't an integer n such that 0 times n is equal to 1. As the inverse axiom fails, in this instance, the set of integers doesn't form a group under multiplication. So this was an introduction to the properties of binary operations that can be used to define a group. If you have any questions related to this video, leave them in the comment section below and I'll get back to you as soon as I can. Like I said before, the notes that you've seen here are based on groups lessons, pages 47 to 48, Further Pure Mathematics 2 by Pearson. There's a link to this book just below this video. If you click on that, it will take you to my Amazon store. If you purchase from there, you help build up my channel, so thank you very much. For more maths content, visit mathematics.proofs on Instagram. Thanks for watching this video and see you next time.